today's topic is layout and stick diagram. Let us start. So let us start with an N-channel MOSFET device structure whose cross section has been shown here. And suppose to fabricate this N-channel MOSFET, what we have given is an N-type silicon wafer. But as we know, to make N-channel MOSFET we need P-type substrate. So how to go ahead for that? So first we have to make one P well in this N-type silicon wafer as shown here. Now after making this P well, we have to form two N plus regions which will make the drain and source contact. After that we have to do a oxidation so that we can create the thin gate dielectric under the gate. Here this gate is not made up of metal, but it is made up of the polysilicon as used to be done earlier. Beside this N plus, you can also see another P plus doping has been done, so which will act as an body contact or the substrate contact for this MOSFET. Why we have to make it dope it with P plus? So that it can create a good ohmic contact with this P well. Another thing to be noticed here is that under the gate the oxide is pretty thin as it is expected for the gate dielectric. However, if you see on this side or this side, here very thick oxides are used. These oxides are called as field oxide. These oxides are expected to be pretty thick. It will provide isolation between this metal lines and this silicon wafer. At the same time, thick oxide also reduce the capacitance between this metal and this silicon. For this MOSFET, what is the channel length? Yes, this is the channel length for this MOSFET. What about the width? Width we cannot show in this 2D diagram, but width will be in the Z direction, which probably we can show in a 3D diagram as shown here. So width is this one and this is the gate length. So as you can see, the same polysilicon gate has been also been shown here. Okay, and this polysilicon gate may be connected to the another gate of another MOSFET which might be lying on this side. Here also you can see the under the gate the oxide is pretty thin, but the on this side on which this polysilicon line will be lying, the oxide is pretty thick, which will act as a field oxide. Now to create a contact or to connect the source and drain to the outside world, we need to have metal contacts from the source and drain sides, as not shown here but it is shown here. So these lines are the metal contacts, and for N channel, as you know, the source and body has to be shorted, so we have shown here, and generally it has been grounded. Now try to think about it. If you see from the top for this structure, or if you think about the top view for this structure, how does it look like? Probably it will look something like this, right? Where this is the polysilicon gate and this is also here the polysilicon gate. This is the total region, which is this N plus diffusion region. So this is the region, N plus diffusion region, right? Okay. Beside that you have another P plus diffusion region. So this is another P plus diffusion region to form the body contact. Yes. Then we have the metal lines from this drain. We have metal lines in drains, we have metal lines connecting the source and body, we have metal lines connecting the source and body. Now here you can also notice there are these black boxes, okay, denoted as this drain, source and body, which indicates the contact between the metal and this diffusion region. This is for diffusion region N type, this is for diffusion region of P type. The width, this width of this polysilicon gate, this will define the gate length for this transistor, right? And this width of this diffusion will determine the width of this transistor, right? And this particular diagram is called the layout of this n channel MOSFET. So if you see from the top how the total structure will look like. And in a particular layout, when the polysilicon line will cross one diffusion region, then only one transistor will form. Please remember that this will be useful for our next discussions. Also, you can see here we have mentioned this metal line as this metal one. That is because this indicates that this is the first layer of metal that has been used to directly connect this drain and this source contacts. But as you know, in a VLSI circuit, there will not be only one metal line that will be used. There will be many such metal lines. For example, in TSMC 180 nanometer technology node, there 6 metal lines, one top of the another, will be used, as well as there will be an additional polysilicon lines. So total there are 6 metal lines and 1 polysilicon lines. So this metal one indicates the first line of metal. This is the layout for one n channel MOSFET. But what about a layout of a particular circuit? For example, let us consider a very simple circuit which is an inverter. So whose cross-sectional view has been shown here, device structure has been shown here. Okay, but notice here that instead of this N silicon, now we have given this P silicon. So as we have given this P silicon, okay, so to make this n channel MOSFET, we no need to form another P plus another P well as we have done earlier. We can directly make n channel MOSFET on top of this P substrate. That has been, you can see it here. Beside that, you can see this another same thing, P plus substrate tap. So here this is the source and drain, these are shorted, and they has been connected with the ground. This is the gate and this is the drain. Let us see for this P channel MOSFET, as the substrate is of P type, and to make P channel MOSFET, what we need to create now, here we have to create one N wells first. So that has been created here first. Then this P plus drain, P plus source region, which will form as here drain and here source. This source is now has to be connected with another N plus region. This has to be shorted, connected with the VDD, and this drain of this PMOS and this drain of this NMOS has to be shorted, as you know from this circuit diagram of an inverter, as also seen it here. Okay. If you see this circuit diagram, so here you know that generally we write here 2, here 1, which indicates that this P MOSFET width has to be 2 times that of this N channel MOSFET, which is due to the lower mobility of hole in P channel MOSFETs. And as you have noticed earlier, this P width here we cannot show in this diagram because it will be in the Z direction, but you remember for P channel the width has to be 2 times that of this N channel MOSFET. And in this context, I would also like to say that you can see both these gates are also shorted because inputs has been applied here. So these 2 gate also has to be shorted by something in a Z direction. Now try to think about how the layout of this inverter will look like. Probably it will look something like this. So for first P channel, we have this N well. So you can see this border lines which denotes this N well. Inside this N well, we have to create this P plus diffusions using this red lines, red block. We can see this is the P diffusions. For N channel, we have this N plus diffusions. For N channel we have this N plus diffusions. Then we have the gate which is crossing polysilicon gate crossing from this P channel to N channel, forming here P MOSFET and here N MOSFET. So same polysilicon gate line has been used here. Remember, this is the metal lines, okay, and this is the contacts between the metal and the diffusion layer, between the metal and diffusion layer. This blue metal will be also connected. This two metal is also connected here. Okay, can we connect this with this? Yes, right. So here this is the supply lines, these two, this is the VDD line and this is the ground line. I hope that you have also noticed that the width of this PMOS is been 2 times that of this NMOS. Besides, we can also see some dimensions are also written here. For example, this 2 lambda, 6 lambda, again here 6 lambda. So what are these dimensions? These dimensions are the dimensions of this layout. Remember, this layout represents the actual dimensions of the device on the silicon substrate. So from the foundry, they have provided certain rules which is known as this layout design rules, and the designer has to obey the design rule and make the layout structure so that the circuits can reliably be fabricated in semiconductor foundries. Regarding design rules, we will discuss about that in bit more detail in next few slides. But for now, I just want to mention you that this design rule specifies what will be the width of this metal, what should be the width of this polysilicon line, what should be the extension of this polysilicon line beyond this diffusion layer, what should be the separation between the diffusion layer edge and this NOL edge, from this NOL edge to the metal edge, all these things. To show you one example, so you can see it here, like for metal 1, what should be the minimum thickness, what should be the separation between them, what should be the separation between thickness, separation and width of this metal line 2, then what about diffusion layer, polysilicon layer. Not only this, even what should be the it also defines the metal 1 and diffusion contact, the dimensions of metal 1 and polysilicon contact, metal to metal via contact, all these things. Yes, and regarding layout, how can we define this layout? Layout can be defined in the following way. So I am reading it here. So layout is an representation of an integrated circuit in terms of planar geometry shapes, which corresponds to the patterns of metals, oxide and semiconductor layer that make up the component of an IC. So it's the definition of this layout is pretty straightforward, and as mentioned earlier, this layout describes the actual layers and geometry of this geometry on silicon substrate to implement a function. Function means in digital IC a Boolean function. So in fabrication of any IC, we need lots of marks for fabrication. These marks are required for fabrication of any IC, and the dimension on these marks will be actually transferred to the substrate. So in other way, we can say that the layout design is basically the design of these marks, because using these marks only you will pattern this metal, oxide or the semiconductor layer as required for fabrication of this IC. And the minimum dimension on these marks will determine the transistor size, right? And the transistor size will determine the speed, cost and the power associated with that particular IC. So design of these layouts are guided by different rules which are known as layout design rules. So these rules has been introduced in order to create reliable and functional circuits on small silicon area. And generally, design rules are usually described in two ways. The first rule is known as lambda rule. The second rule is known as micron rule. In lambda rule, all the layout constraints is defined in terms of a single parameter lambda, okay, which allows us a linear proportional scaling of all geometrical constraints. One example of this lambda based rule is the MOSIS or MOSIS, which has been used for designing this CMOS process flow. Now, using this lambda based design rule, suppose for this metal 1 to diffusion plane contact, suppose for this it has been defined as the separation between this edge and this edge has to be 1 lambda. Then if you switch the technology node from 4 micrometer to 2 micrometer, then only the value of lambda will change. Okay, so you can say this, then the 1 lambda or this 2 lambda is terms of some general, and it will only change, the value of lambda will only change with change in the technology node. So this MOSIS, which is a lambda based design rule, can easily provide the scaling. However, this MOSIS or MOSIS, which is a lambda based design rule, cannot be directly used for submicron CMOS process. Okay, it is not that straightforward for submicron technology nodes. On the contrary, for micron rules, all the device features will be stated in absolute dimension, which is given in the unit of micrometers. So suppose for this the same contact, if you have to use the micron rule, then instead of using this 1 lambda, you need to use probably 1 micron for some technology node, maybe in 0.8 or 0.7 micrometer for another technology node, like that. So from this also you can easily understand how lambda based design rule can provide easy scaling. So here one question might be arise in your mind, what is this lambda? Lambda is a specific length for a particular technology node, and the minimum feature size for a particular technology node will be given by 2 lambda. Okay, let us now spend some more time to understand or to see how this MOSIS rule can guide us for a CMOS process flow. So in this slide it shows the MOSIS layout design rules, which shows like active area rules, polysilicon rules, metal rules, contact rules, and these are not the complete design rules given by this MOSIS. You can find it in the website as well as in your Kang's book. Okay, so for example, this polysilicon design rule, it shows that the minimum polysilicon width one have to be in particular technology node, it has to be 2 lambda. Minimum polysilicon spacing has to be also 2 lambda. Minimum gate extension to this, like that, 2 lambda. Metal rules, polysilicon contact size has to be 2 lambda. So using this, they have also provided one layout, one schematic layout, which is shown here, and all these constraints, this R1, R2, R3, so you can see all these things are indicated here. I request all of you to please spend some time and see how this design rule has been incorporated here. One more request to all of you is to make a layout design of a simple CMOS inverter, okay, using this MOSIS layout design rules. Please do it use your full paper to design this MOSIS, to design a layout of a simple CMOS inverter. Please remember, you need to take care of the substrate contacts for both PMOS as well as NMOS in that particular layout. So far we have discussed the layout of only CMOS inverter, where we have one NMOS and one PMOS. What will happen if we have more than one NMOS and PMOS? For example, in case of 2 input NAND or NOR gate, as you can see here, For this case, two PMOS are in parallel and two NMOS are in series. However, for this case, two PMOS are in series and two NMOS are in parallel. So among them, let us first focus on the series case, where either two NMOS or two PMOS are in series. So what do you think how their layout will look like? It's easy, right? So it will be something like this. This is one diffusion. It might be P diffusion or N diffusion, depending on that it is whether it is PMOS or NMOS. So this is one diffusion. This is another diffusion. This is the polysilicon line for gate A. This is the polysilicon gate line for gate B. So this is actually gate A, transistor A, and this is actually transistor B. These are the metal to diffusion layer contacts, this black one, right? So we can see this metal contact is here, as well as this metal contacts are here, and metal contacts are connecting these two transistors. But if you can think this structure or this structure here, these drain and this source, they are connected, they are shorted, okay? And as a MOSFET is a symmetric device, so what if we can think of, like, instead of having two separate diffusion region, if we have a diffusion region something like this, that is, we can use the shared diffusion region for both this transistor A and transistor B, then that will serve the same purpose, right? Correct. Now the question is why we should do that. Okay, the reason is, you remember, right, as discussed in the class, for this MOSFET we have a parasitic drain capacitance here, we have a parasitic source capacitance here, which are nothing but due to the diffusion capacitances. So more the diffusion area, more will be the parasitic capacitance. So if you can reduce the area like here, so we can significantly reduce the parasitic capacitance, which can give rise to higher speed as well as lower power dissipation. Eventually, if you do not need any contact from here or from here, you can think of removing this, even the metal to diffusion layer contact, like here, which is called the merge diffusion, where we can further reduce the area of diffusion, and as well, that means basically you can further reduce the diffusion capacitance or the parasitic capacitance. So if more than one transistors are connected in series, we can do simply this type of configuration and simply put a single diffusion layer, and in perpendicular to that, this polysilicon lines, which will construct the transistor. Clear? Right. So what will happen in case of this parallel combinations? Here two parallel PMOS and here two parallel NMOS. It's not difficult, same as like this. So here also we will use one single diffusion, right? And these are, we will use two gate contacts, these polysilicon gates, this gate A and gate B. Okay. So we can see for this case, this drain and this drain, they are shorted. So we can think of these two gates as a you use this type of shared diffusion for this, right? And for this top, the source and this source, okay, they are connected with VDD. So we can think of this is connected with the metal, this is connected with the metal, and this metal is connecting like this. So this is how we can this is how the layout of transistors will look like if there are more than one transistors and they are connected in parallel. I hope you understand this part. Yeah. Now let us consider a 3-input NAND gate as shown here. 3 inputs A, B and C connected in this fashion. So how the layout diagram will look like for this 3-input NAND gate? We can do it, na? Let us see how does it look like. So probably it will look something like this. So again, this is this N well, you remember, this is the P diffusion, this is the N diffusion. Okay, these are the three polysilicon lines, A, polysilicon line B, polysilicon line C. Where this polysilicon line cross these diffusion lines, there only one transistor will form. So this is transistor A, PMOS, transistor B, PMOS, transistor C, PMOS. Here transistor C, NMOS, transistor B, transistor B, NMOS, transistor A, NMOS. Now let us see the connections, how they are connected. So you can see from here, this A, PMOS, B and C, all of them, their sources are connected with the VDD. So let us see that. This is VDD. So for transistor A, its source is connected with VDD, is fine. For transistor B and C, this is a shared source. So this is connected also with BCC, VDD. So that is fine, right? Okay. What about the other terminal, drains? So three drains are now shorted, connected with the output, as well as it will be connected with the drain of CNMOS. Let us see that whether that is happening here or not. So the output which is coming from the drain terminal of C, that is basically this one, this is now coming here, and it has been now connected with the drain of NMOS, which is basically CNMOS. That is also correct. And you can see this is the output Y, this output Y, and output Y is connected both with transistor A as well as transistor AB as well as transistor C, as you can see from here, all PMOSs. Okay. Now let us consider for what is happening in case of this NMOSs. For NMOS, this transistor A source is grounded. So this is transistor A, NMOS, and its source is now grounded. It looks fine. Okay. Now the drain of NMOS A is connected with the source of transistor NMOS B. So this is the source of transistor B. This is also the marged diffusion, and you can see this is for this B, that is also fine. Similar, same thing is also happening here between B and C. You can see also it is happening here. C, this part we have also contacted here. So this is quite easy. So if any circuit now has been given, you will be able to draw its layout diagram. But be careful, for drawing layout diagram, you have to maintain all these dimensions very carefully. All these separations and all these things, separations, width, the distance between these two edges, everything you have to do it carefully. So it is very easy to guess then this drawing a layout is a very time consuming process. That is right. So fortunately you don't have to do that manually, or as a designer we don't need to do it manually. The software will do it for us. And if you have noticed it carefully, at this caption of this figure we have written 3 input NAND standard cell gate layout. Okay, what is this standard cell gate? This is one of the layout style that generally been used. So there are generally two popular layout styles are there, as you can see in this slide. The first one is this Weinberger layout technique, and the second one is the standard cell layout technique. So in this Weinberger layout technique, what is happening, the data line wires, you can see here, these all the signal lines, the inputs or maybe the input or the output, these are routed parallel to the supply line. So you can see these are the supply lines, VDD and ground. So signal lines are also parallel with this supply lines, VDD and ground, and obviously this has to perpendicular with that of this diffusion areas, that is perpendicular to the diffusion areas. Whereas in case of this standard cell layout technique, the signals are routed in polysilicon line perpendicular to the power lines. So you can see it here, these are the power lines, VDD and ground, and the polysilicon lines which are basically forming the gate here, they are perpendicular to that of these power lines. And also, as the same polysilicon lines can be used as a gate for both PMOS as well as NMOS, So this standard layout technique results in a denser layout. By the way, can you tell this is the layout of which gate? Yeah, please figure it out by yourself. I am not going to tell this. But whatever layout style you may use, but any layout to draw any layout, it is you need to spend good amount of time, because all the you have to maintain all these dimensions, separation and all these things. To solve this issue, another technique has been invented which helps us to plan the cells and estimate the area even if before we do the careful full layout. This particular technique is called the stick diagram. These stick diagrams are easy to draw because we don't have to draw them in scale. At the same time, in stick diagrams, wires and transistors are represented in dimensionless object, and their position is relative, not absolute. For example, let us see a case as shown here. Same case, a layout of 3 input NAND standard cell gate layout. So if this layout is being just presented in stick diagram, it looks something like this. Here it is VDD, one line, ground another line, diffusion one single line, P diffusion another one single line, N diffusion one single line, polysilicon 3 lines, metals connected like this. In stick diagram, the particular widths, their thickness are not important. We can just simply represent them by using only lines. So here you can see, for this example, these dashed lines are being used. You can even use some color lines to represent this VDD, this metal lines as shown here, metal contacts, P diffusion, N diffusion, all these things. I will be showing you in the next slide, that one. So, and here also you can see the positions, they are relative. You don't have to do it dimensions. So here it is drawn everything in dimensions. Here you see we just simply draw 3 lines. This very simplistic representation of this layout, so which can be drawn very quickly. Let us see some more examples of stick diagram. For example, this is an inverter. How its stick diagram will look like? It's just simple as it is. This VDD, ground, this line connected, P diffusion, N diffusion, polysilicon line, metal layers connecting this drain and drain. That's all. Just notice the color code that generally been used. This blue lines, orange, green, red line, and then blue for metal lines. Okay. What will happen in case of NAND 2? This is a NAND 2 gate or 2 input NAND gate. For 2 input NAND gate, it will be looking something like this, right? Here this indicates all PMOS are in parallel, and this indicates all NMOS are in series, and then you have to connect it. Okay, I hope you are able to correlate this directly from here to here and this here to here. Now, if any other Boolean function has been given to you, can you draw its corresponding stick diagram? For example, let us see this Boolean function, f equal to a plus b dot c whole bar. So this is the circuit representation of this Boolean function, right, in using CMOS. So its stick diagram will look something like this. Here it is VDD, ground, P diffusion, N diffusion, A, B, C, three polysilicon lines. Where this polysilicon line will cross the diffusion, it will form the transistor. So PMOS A, PMOS B, PMOS C, PMOS NMOS A, NMOS B, NMOS C. So once you draw up to this part, then you have to think for the connection. For example, let us consider this pull-up network. For this pull-up network, this A and C, both of their sources connected and connected with this VDD. So this is transistor A, PMOS. Its source is now connected with the VDD. This is the source for PMOS C, whose source is also connected with the VDD, right? Okay. Then the C, the other terminal, that is the drain, is connected with the output. Okay. C, the other terminal, that is this one, is now connected with the output. That is, here it is represented as X, but you can see that is a F and X are actually the same. These are output. We can also see the output F is also connected with B. So here also this output, this is the output is connected with B drain. So that is also fine. And A drain is connected with the source of B. A drain is connected with the source B, right? Merged diffusion, you remember? So this is fine in terms of this pull up network. Okay, what about this pull down network? So for pull down network, this output is now connected with C. This output connected with the source, connected with the drain terminal of this C. The output is now connected with the drain terminal of C. The other terminal of C is now connected with the drain terminal of both A and B. The other terminal of C, that is here, this is connected with the other terminal, with the drain terminal of B, that is fine, and the other drain terminal of transistor A. So you can see the transistor connected with the transistor A. For NMOS A and B, their sources are connected and grounded. For NMOS A and B, their sources are connected and grounded, right? So this we have a cross checked that all the connections which is been given here is actually matching with this stick diagram, so it looks fine. But see here, we have used the ordering of gates in this fashion: A, B and C. Is there any reason? We could have used in a different fashion. For example, we could have used the ordering of this gate like A, C, B. What is the difference? So suppose if we connect it like A, C, B, then again the how to draw it? Same thing. First this, then this, means first VDD, then ground, then this P diffusion, then this N diffusion. Okay, then these three lines written, which three polysilicon lines for gates which are A, C, B. For this particular ordering of this A, C, B for these gates, what will be the connection? Now check the connection. Now A and C sources are connected with VDD. Transistor A and transistor C, that is this, their common terminal, this is source, this is connected with VDD, that is fine. The other terminal of A is connected with the B, so other terminal of A is this, it has to be connected with the B, that is also fine. Okay, now the other terminal of B has to be connected with the output. The other terminal of B, that is this one, this is now connected with this output. Okay, please remember here is a small thing need to be changed. This F here represents output and here it has been shown by X. So basically X and F are same thing here. Now with this B terminal, C, other terminal of C, that is the drain terminal of C, should also be connected. So C, other terminal, this is also connected with the terminal, this terminal of B, that is also fine. So pull up network is fine. Now let us concentrate towards this pull down network. Okay, for pull down network, see here, let us consider from here, start from here. The output is connected with C, the drain terminal of C, and only with C. So the output which is coming from here if it has to connect here, then there this this n diffusion has to be broken, because you see here the output is only connected with this C. So the output has to be only connected with C. Okay. Now this C other terminal, that is C this terminal, this has to be connected with both A and B. So this is already connected with A, and now this terminal has to be connected with this terminal of B. The other terminal of B has to be grounded. Other terminal of B is grounded. Other terminal of A is also grounded. Other terminal of A is grounded. So we have now cross-checked that these connections shown in this stick diagram is matching with that of this circuit. But we have to notice one thing. For this case, for both N diffusion and P diffusion are continuous, are unbroken. But for this particular combination of ordering of gates A, C, B, we can see the P diffusion is continuous, but the N diffusion line is broken. So what does that mean? When you have a broken diffusion line, we have seen in terms of layout that from one edge of this diffusion edge to the other edge of this diffusion, there has to be some minimum separation, so there has to be some gap. So basically you are losing in terms of device density, which is not desired, in terms of device design. So the question to be asked, is there any technique which will tell us like what should be the correct order of these gate inputs, whether it is ABC, BCA or ACB? Yes, there is a technique. The technique is called the Euler path technique. So for example, for the same circuit, let us see how the Euler path will help us to determine what should be the correct sequence of gate inputs. For constructing this Euler paths, first we have to see draw its logic graphs. So how to draw logic graphs? In logic graphs, the edges are represented, the edges represent the transistors and the vertices are nodes of this network. For example, if we draw the logic graph for this particular circuit, it will look something like that. And here we have to draw the logic graph separately for pull down network and pull up network. As you can see here, this is the circuit representation of pull down network, and this is circuit logic graph for pull up network. So let's check that with F. It is for the pull down network, in the top side is F connected with C, then A and B, then A and B are connected, other terminal is grounded. Okay. For this pull up network, it has to be drawn something like that. This side VDD and this side is the output F. This side VDD, this side output F. So this is A, B, and the other side is C, in this fashion. Now we have to search for the Euler path in this logic graphs. So what is this Euler path? Euler path in logic graph is defined as a path through all nodes in the graph such that each edge of the graph is only visited once. For example, let us see for this. Let us see for this green one, that is the pull down network first. Let us see a path ABC. So starting with A, go to B and then C. So in that way we have traveled through all these edges as well as all nodes, right? But we have not traveled to a single node more than once. So this indicates that one Euler path exists for this pull down network. What about the pull up network? For pull up network, A, B and then C. That is also fine. So for both pull up network and pull down network, Euler path exists when the input gate combination is A, B, C. Okay, but now if we choose the other combination like ACB as we have done in the last slide, then let us see for the pull up network first. For the pull up network, if we choose ACB, A, fine, B, C, fine, B, fine. So we have an continuous path from here. So we have an Euler path for this pull up network. What about the pull down path? pull down network. So A, C, yeah. Now once we go to C, we cannot come to B, right? So we cannot travel this B. So we don't have an Euler path for this pull down network if we select this combination gate order ACB. So for this particular, that's why you remember, for this particular gate order as shown earlier, though there is a continuous line or p diffusion line for this pull up network, the n diffusion line, which is represents this pull down network, was broken. So by using this approach, you should be able to find what is the correct order of this gate inputs for drawing any stick diagram. Another example, draw the stick diagram for the following circuit. So this is another circuit implemented using CMOS, and we need to draw this stick diagram. So to draw the stick diagram, first we have to draw the logic graph. So logic graph for individually for pull down network and pull up network. So pull down network, for this it will be looking like this: X output, this. So this X, one side it is D and B, one side it is D and B, other side it is C and A, other side it is C and A. For this pull up network, it is VDD and output, it is VDD and output. One side we have this C and D, one side we have C and D, on the other side you have A and B, on the other side we have A and B. Suppose you choose a path like this: A, B, D, C. So if you choose a path A, B, D, C, A, B, D, C, so we have an Euler path for this pull up network. What about for the pull down network? A, B, D, C. We too have an Euler path for this pull down network. So A, B, D, C, this order can be used for drawing the stick diagram as shown in this diagram. So here it is VDD, ground, N diffusion, P diffusion. This is the polysilicon, 4 polysilicon lines for gate A, B, D and C. So these are the metal connection, this is the output, and these are the internal connection. I request you, as we have discussed in the last slide, please check that all the connections shown in this stick diagram with respect of this circuit. So I hope this gives an good idea to you how to draw a stick diagram for any Boolean function represented using CMOS